Okay, let's look at the proof of Theorem 14. So let f be a vector function or a force field. The following conditions on f are equivalent. So for any oriented simply closed curve, we have the integral, line integral is 0. That's condition 1. Condition 2 is for any two oriented simple curves, C1 and C2, that have the same endpoints, we have integral over C1, line integral over C1 equals line integral over C2. And the third condition is if big F is the gradient of some small f, that means big F looks like this. And it is mentioning simple curve, so let me just define where the simple curve is. So a simple curve does not cross itself. So this first guy here would be simple, but this figure 8 guy would not be simple because it crosses itself right here. Okay, so what we're going to do here to prove this, we're going to show that 1 implies 2. Then we're going to show that 2 implies 3. And then we're going to show that 3 implies 1. Okay, so let's do that. So let's start by proving 1 implies 2. So let me erase the theorem and we'll look at the proof now. Okay, so let's prove that 1 implies 2. So let's take two oriented simple curves with the same endpoints. Okay, so let me draw a picture what these would look like. So here's the picture. So they're starting here, going up to here, both of them. Starting at this endpoint, going up to this one. Okay, I want to change this into now an oriented simple closed curve. So let me draw another picture beside it. So I drew the same picture over here, but in the first picture they're both going up this way. So I want to reverse the orientation in one of them. So I want to say the orientation this guy to be switched around. So we just put a minus sign in front, would switch the orientation around. So now it's going around the simple closed curve. So note if I let C equals C1 minus C2 now, C is a simply closed curve. Now we can use our assumption that 1 is true. So pretty much 1 is saying that the line integral over C then should be 0. Okay, let's write that. Yeah, so now since we're assuming 1, it says that the integral over a simply closed curve should be 0. So we'd have this condition. But then by properties of integrals, you can break this up as integral of C1 f dr minus integral of C2 f dr. And that has to equal 0, so it's equal 0. So you can just add this to both sides. So this implies adding the integral of both sides, we have this. So hence, we have shown 1 implies 2. Okay, now let's go 2 implies 3, so let me erase some things here. Now let's prove that 2 implies 3. So it's a bit trickier, this one. So let's consider path 1. Say it's going along the x-axis, then y-axis, then up the z-axis to get to the point x, y, z. Let's parameterize each of these guys. So C1t. So we're starting at 0, 0. 0, or 3 dimensions here, and then we're ending up at this point here. It'd be x 0, 0. So minus 0, 0, 0 times our t. So if you work this out, you'll just get xt 0, 0, and again t goes from 0 to 1 when you parameterize these lines, and c1 prime then would just be x 0, 0. Okay, that's our C1. C2, well, that one we're starting here. So we're starting at be x0, 0, 0. And we're going up to, at this point here, it'd be x, y, 0. So it'd be x, y, 0 minus x, 0, 0 times t. And if you simplify this one, you'll just get x, yt, 0. Again, t goes from 0 to 1. And then you'll have your c2 prime will just be 0, y, 0. And lastly, let's do the c3 guy. So C3, you're starting at x, y, 0. So starting here, it's x, y, 0. And we're ending up at x, y, z. So let's just subtract our start point times t. So if you work this one out, you'll get x, y, z, t. So then C3 prime will be 0, 0, z. Okay, so let's keep going. We're going to now actually do the line integrals over these. Okay, so I wrote my C1, C1 prime, C2, C2 prime, C3, C3 prime. So we're going to do the line integral over our path 1. So it'll be the line integral over C1, over C2, over C3. But up here, our C1 prime is x, 0, 0. Our C2 prime is 0, y, 0. And our C3 prime is 0, 0, z. So it's going to pick up the I component of f. And f is the I, j, k over here is going to pick up the m guy. So the first one will be integral 0 to 1. So it's going to be the I component times x evaluated at C1, which is x t 0, 0. So it's going to be m x t 0, 0 times x times dt for that one. Then the next one is picking up the j component because their I and k are 0. So it's going to be the j component, which is the n guy, evaluated at our C2. So our C2 is x, yt, 0. So it's going to be n x, yt, 0 times y dt. And lastly over here, 0 to 1. This is picking up the k component because there's 0 in the I and j here. The k is the p, so it's going to be p evaluated at C3. It's going to be p of x, y, z, t times z dt. Okay, so let's keep going from here. So we have this. I'm going to call small f the integral over path 1, which is shown was equal to this. Now I'm going to make a substitution in this last integral here. I'm going to say let w equal zt. So then dw dt equals z. So then we can have dw then equals z dt, which I have right here. Be my dw. So looking at this guy here, over here, this then will equal integral w of 0, w of 1, p x, y, w, dw, and w is 0 is 0 and w1 is z. Okay, so now let's take the let's take the derivative with respect to z on both sides. So doing that, you'd have fz on this side from this guy up here. Now the first integral doesn't have any z, so that's going to be 0. So it'll be 0. This one doesn't have any z either, so it'll be plus 0. And this last guy is equal to this one over here, so it'll be plus derivative with respect to z of integral 0 to z p x y w dz. Okay, so by the fundamental theorem of calculus, then partial respect to z, while you're taking a derivative, and then you're taking an integral over here, it's just going to be p x y z. Okay, so we got that. Now let's keep going. Okay, next we're going to consider path 2. So we're going to end up at the same point. We're just going to come from a different direction this time. So we're starting at the origin. So we're going to go along the z-axis first. Then we're going to go along, so this is the x here. Then the x, then the y. Okay, so C4. You're starting at 0, 0, we're going to 0, 0, z. I'll let you check when you parameterize this, 0, 0, zt, so C4 prime, then this would be 0, 0, z, and C5, well here you're starting at 0, 0, z, 0, 0, z, and you're going out to x, going on the x, it'll be x, 0, z minus start point times t. And let you check when you simplify this, you just get xt 0 z, so c5 prime would be then, derivative of this guy would be just x 0, 0, and c6 so that one you're starting at x 0 z, and you're going to x y z. So when you simplify that, let you check, you get x y t z. So then c6 prime would be 0, y, 0. Okay, so let's keep going. So note here, P1 and P2, the two paths, they both start at the origin and they go up to the point x, y, z. So the same starting point and ending points. So by 2 then, the line integrals over these two paths should be the same. Okay, so make that observation. So let me erase this now. Okay, so we can say that small f equals the integral over P2 because again, by property 2, we're assuming or condition 2, the integral over P2 and P1 are the same. Okay, so let's do this integral here. So the C4 prime guy is picking up just the k component here. So it's going to be integral 0 to 1 of P evaluated at 0, 0, zt, so 0, 0, zt times our so C4 z dt plus this one C5 prime is picking up the I component, is in the I position, it's going to be the m guy, it's going to be m at C5, so C5 is here, bx t 0 z x dt, and last one So the last one we have then the C6. Okay, so it's going to be in the J component, so it's going to be N. It's going to be N X Y T Z dotted with this will be Y dt. Okay, and we're going to make a substitution in this guy. It's going to say let W equal YT. So then d W dt equals Y. So then dW equals Y dt. So let's look at this guy here. Bring it over here. So that guy would be integral W of 0, W of 1, be N, X, W, Z, dW, and W of 1 is Y, W of 0 is 0. Okay, now we're going to look at the derivative then. So it'll be small f with respect to y this time. Okay, so this guy doesn't have a y, so it's 0. This doesn't have a y, so it's 0. And using the FTC in this like we did on the other one, it's just going to be end up being n x y z. Okay, we've one more path to look at. So lastly, going over path 3, so going along the z, then y, then x. I won't go through it, but you can go through it and show it'll end up being small f x y z will end up being this guy here. Now, if I take derivative with respect to x this time, that is no x, so it's 0. That is no x, so it's 0. And by the FTC, when I take this derivative with respect to x, it will be m x, y, z. So hence we've shown that big F looks like small f here, or small f x I plus small f derivative with respect to y j plus small f derivative with respect to z k, which is then the gradient of small f. So hence we've shown that 2 implies 3. So what's left to show now is that 3 implies 1. So let's do that. So lastly, let's prove that 3 implies 1. So suppose that f is the gradient of some small f. That means that you have this condition here. Let C be a simply closed curve, and parameterizing the curve is r of t equal xti, ytj, ztk on AB. So integrating over C then, so pretty much to show that 3 implies 1, we need to show this is 0. Okay, well by definition it's equal to this. And then that equals this guy over here. Okay, so let's keep writing this out. So then you can write this as integral a to b. I'm not going to write the r of t out again here. I'm just going to write, say, fx dotted with dx dt. Then this guy dotted with this one, dy dt. And then this dotted with this one. So it'd be f z dz dt dotted with dt. So by the chain rule then, so by chain rule, so theorem 10, this stuff inside here, that's just the derivative of f with respect to t. So this then equals integral a to be the derivative with respect to t of my f but you're integrating a derivative here, so it's just going to be then f of, well, putting your d should be x of t, y of t, z of t, that's fine. I was leaving off the t's for ease of notation. So when you put in b, it's going to be f of r of t, r of b, and then minus f of, putting in a, f of r of a, but this equals 0 since we're assuming that, up here we're assuming that our C was a closed curve. That means that R of A equals R of B. So since R of A, so R of B equals R of A. So hence 3 implies 2. Okay, so we're done with Theorem 14 now, because we showed that 1 implies 2, 2 implies 3, and 3 implies 1. So we're done.